So what I'm going to be talking about here is some of the work that we've done based on the MESSENGER results to identify what the darkening agent is hopefully on the surface of Mercury. And I guess the spoiler is that we believe it's carbon, which is why we're here in this session here. Let me make sure I can advance the talk here. So when we first got to Mercury, we were expecting to find something like ilmenite or an iron or titanium-based phase darkening the surface. We knew that it was very dark from telescopic measurements. We knew that it was very dark from the Mariner 10 observations. We also knew the slope was very reddened. All of this seems consistent with an iron or titanium-bearing phase. However, we didn't see any evidence by a telescope of a 1 micron band, which is typical in iron-bearing silicates. So there was no clear evidence for olivine or pyroxene or other minerals, iron-bearing minerals that we have on asteroids or on the moon to account for some of the darkening. So we assumed that this was probably because there's intense space weathering at Mercury, or that we just didn't have the resolution to see in pressure craters where the absorption band hadn't been obliterated. When we got to Mercury with MESSENGER, however, we looked all over the place, basically. We looked in fresh craters, we looked in crater rays, we still didn't see any sign of obvious mafic absorptions. And we also looked at the surface with geochemical instruments, so the gamma ray and X-ray spectrometer, and neither of those found substantial amounts of iron or titanium. So we were basically left with this situation where we have a very dark surface, almost as dark as the lunar Maria on Mercury, but really not very much iron or titanium observed on the surface. So that left us with carbon as the most likely darkening agent on the surface. I keep hitting the incorrect button to advance here. So on the surface of Mercury, in addition to just the surface as a whole being darkened, we have these exposures of what we call low reflectance material, which is the darkest of the material on Mercury. And we see it excavated by craters, we see it excavated by basins, and we see some kind of regional areas that are darker and bluer than the rest of the material. So when MESSENGER reached its final stages and was going to be soon crashing into the planet, we looked at whether there would be an opportunity to observe some of these very dark materials in the low altitude flyovers. Because, as you've just heard from Alessandro, carbon is really tough to characterize through reflectance or even emission spectroscopy because there's not a very strong prominent absorption band. There's kind of this weak curvature, which I'll show a few spectra from Mercury, from the ratio spectra that he referred to later. Unfortunately, I don't have our lab spectra of graphite that we used for the spectral modeling in here, but it's, I refer to it as a 600 nanometer band, but it's really a very broad, shallow absorption that kind of stretches from 500 to 800 nanometers in the fine-grained graphite. So it's, seeing the kind of minimum around 500 doesn't bother me too much in his laboratory spectrum because it's more this curvature that we're trying to characterize that is, it is indicative of graphite, but there are other minerals such as ilmenite that do have a similar curvature. But of course, we ruled out ilmenite by the lack of titanium or iron. So anyway, we had this opportunity to do some neutron detector measurements over these low reflectance material rich terrains. So in these flyovers, we identified 3 areas that had an increased abundance of low reflectance material relative to the surroundings. And the response of the neutron detector basically goes the opposite way, whether you have carbon or whether you have iron. So this was a good opportunity to test whether there was a suppression or a increase in the neutrons over these low reflectance materials. And these data are presented in Peplowski et al. 2016. I won't go into a ton of detail about them because I think I've already wasted a lot of time on my first few slides. But the bottom line is that they detected an enhancement of between 1.5 to almost 3% carbon over these low reflectance material regions on the surface. So here is, these are in the northern hemisphere because that's where we passed closest to the surface. And these were unfortunately the only regions that we were able to get the counting statistics to directly measure carbon from orbit. So what I've been working on is trying to map this low reflectance material across the surface of Mercury and to try to extrapolate these measurements to other portions of the surface to see how globally pervasive it is and where it comes from across the surface. So here's a color composite of Mercury with using principal component analyses, which because the spectra, as you can see in the corner, have very little differences other than the slope and the albedo, these kind of tease apart differences in the spectral properties in the MDIS or the masks data. And this is looking at the red channel is principal component 2, which basically captures a lot of this curvature and slope. The green channel is PC1, which basically is albedo. And then the blue channel is, again, trying to pull apart this slope. So the materials that are very blue have basically a shallower slope than the rest of Mercury. They're very dark, so very low in the green, and they're on the lower side of the PC2 continuum, which the PC principal component 2 is just a shape, basically. And so the low end happens to be the ones that correlate with low reflectance material. All right. So basically what we did is we looked at the low reflectance material and we derived different thresholds for this where the lowest reflectance material was located. And in the initial constraints that we placed that we used for targeting the materials for the neutron detector, do I have a pointer here? I don't know, I feel like a spinning ball. For the neutron detector measurements, these are up in here. So there was this measurement here, here, and here. We used very restrictive constraints in order to locate these regions because we wanted to get the most LRM-rich material possible. In my paper that was recently published in GRL, we loosened them a little bit to try to get an idea of the broader distribution of this material. What we can immediately see in this image is that there's much more LRM concentrated in the southern hemisphere where we were not able to make measurements with the neutron detector. But you can also see that around Rachmaninoff here, around Sobkub-Flanatia, around Tolstoy, you can see these kind of annular exposures around basins and craters. That's Basho crater here. So this is the absorption that we're looking at. And again, this is the reflectance ratio that Alessandro spoke about. So because we have space weathering, because we have kind of an unknown mineralogy in the terrain, we're kind of restricted to looking at differences in terrain on Mercury. So what we did is we took high reflectance plains, which are volcanic and kind of the best understood as far as knowing that they're as close to a single composition as possible. And we've ratioed the material on the surface to get at what the differences are between the volcanic terrain and this low reflectance material. And so that's how it kind of pulls out this broad absorption here that kind of centers around 600, but goes down, suppressed it all the way between 500 and 800 nanometers. And so we used this in Poplawski et al. To correlate with the excess carbon as measured with the neutron detector. And you can see here that it's basically a linear relationship between what was measured by the neutron detector and with the carbon on the band depth rather on the surface. So now if we look at this LRM map again, I'm going to plot some different regions here. These are 3 different types of regions. So we've got, this is the band depth map. We've got Rachmaninoff here, we've got Basho and Tolstoy, and then we have this broad region that's south of Caloris. I'm going to speed up because I think I'm quite late. So what we wanted to know is what do these correlate with? What's going on the surface? This is a crater density map from Denevi et al. It's going to be in the Mercury book chapter. And you can see that in these regions with a higher crater density, we do have these broad exposures of low reflectance material. So in addition to these regions where we've got basins and craters excavating low reflectance material, it's these oldest terrains that have the more diffuse exposures of low reflectance material. So here's just some pretty pictures of that. Here's Basho crater, low reflectance material in just a color composite, not a PC composite, Tolstoy, and then at Rachmaninoff. So spectrally, these the regions are quite consistent with one another. There's more variability among the craters and the basins, but they all have this similar curvature when you ratio them to the reflectance planes. And if we take the band depth ratios for these and extrapolate the measurements from the neutron detector measurements, you can see that most of the surface clusters in this similar carbon range of around 2% that we got with the neutron detector. However, there are these very beautiful fresh exposures at Rachmaninoff and Basho crater, which by weight percent are consistent with having almost 5 weight percent carbon in them. So very high abundances of carbon. So when we look at the different hypotheses for where the carbon on Mercury could have come from, there was it was proposed that there could be carbon on Mercury due to exogenic processes, so cometary deposits depositing them over time, causing the overall darkening of the surface. Or it's possible that carbon could have been there from the beginning, and if it was incorporated into the crust and mantle rather than into the core, it would have been stable as graphite and floated to the surface early in the evolution of the Mercurian magma ocean. So while the exogenic hypothesis could occur, could contribute to the overall darkening of the albedo of Mercury, it's not really consistent with the geological occurrence of the low reflectance material being excavated from depth. However, the endogenic hypothesis is consistent with the stratigraphy and this association with the older terrain. So I will stop now before I get a hook pulling me off the virtual stage and let Kathleen tell you more about the magma ocean.
Great. Thank you very much. Thank you very much, Rachel. Do we have a couple of questions here for Rachel?
A lot harder for you guys to make me stop talking when it's
when it's virtual. Yeah, I've noticed. I think we're running behind a bit.
Yeah, sorry about that.
Okay, we have a question. Amanda, go ahead.
Let's see. I'm trying to understand the abundances that you're getting. So, you're getting abundances from the neutron spectrometer, right? And then you're showing they correlate with the band depth.
Right.
Right. And but do the neutron spectrometer data tell you about stuff that's more at depth than what you can see with the spectrometer?
I think in this case the penetration depth is not too deep. So it's possible, yeah, that they could be seeing deeper than the slightly deeper than what we're observing in the reflectance data, but we do see the correlation between the band depth and the neutron data at the 3 sites that we were able to measure. One of the things we want to do is look back at the neutron data and see if there are any other regions where maybe the statistics aren't quite as good, but that try to add some more data points to that plot, because 3 is kind of unsatisfying.
It was a good correlation, though.
Yeah.
But and then you said that you weren't going to show us the lab data, but you have lab data that does show a graphite that has a band there.
Yeah, I mean, it looks similar to what you showed, where it's this kind of broad curvature. So it's not like a strong band. It's very unsatisfying for someone who works with mafic silicates most of the time, because it's consistent with graphite, but not exclusive to graphite.
Right. Okay.
That makes sense.
And
yeah.
but then, are you using those lab data to get out abundances on the surface from the
So we did do modeling at Rachmaninoff. So using modeling at Rachmaninoff with the laboratory data and using a very fine-grained carbon. So we were basically trying to look at if you have fine-grained distributed, it's easier to darken with less. It's easier to darken and change the curvature without just smashing the whole completely darkening. So we were looking at very fine grains, about 2 micron particles mixed in, and it still took about 7 volume% to darken it at Rachmaninoff, which is consistent with the 5 weight% that we're getting in the extrapolation from the neutron data.
But what were you adding your graphite to?
Oh, to a derived spectrum. Basically, we took the high reflectance plane spectrum and mixed it by radiative transfer with the carbon.
Okay, cool. And your paper is coming out soon?
It's out online. I don't have page numbers for it yet, so I don't think it's out. Yeah, so yeah, I'm looking at some of the questions in here. So Diane, the argument against the exogenic was that we see across the circuit, we see it excavated in the ejecta of basins and craters primarily. So there's this geological association with it having been there before all of the volcanic plains were erupted. So it's, if we had to accumulate it slowly over time from comets, it would be really difficult to then bury it all under this early volcanism. And Tom, I don't know about carbides. It's possible. I mean, we need to look at a lot of the spectra and of some of the other organic and carbon species and see if we can constrain something better with that. And I think we need to dig into the UV data more based on having seen Amanda's spectra.
Okay, great. Well, thank you very much. I think we're ready to move on then to the next talk. The role of carbon in exotic crust formation on Mercury.